The Simpletons' proof of the twin prime conjecture using real-world mathematics. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. Looking at the four sequences of cubic quadruples I revealed in my video, Infinite Numerical Integer Series, the secret of the 85-digit cubic quadruple, I noticed in the fourth sequence that resulted from the input of even numbers into equation 3 that the last two cube roots, which will always be adjacent odd numbers, were in fact twin primes, 71 and 73. So I asked myself, will this infinite sequence always throw up a pair of twin primes on the odd occasion, which would constitute a proof of the twin primes conjecture? Running the equations in Precise Calculator gave a resounding yes to the question, as the results on the slide show. We have a 2.23% hit rate out of 10,000 shots, equal to 3.10 times 10 to the minus 10% of the target area. QED, that which was to be demonstrated. There are those who, mainly because it undermines their mathematical standing, will say, how do you know that the sequence with regard to twin primes does not eventually terminate? This is not proof to infinity. As Leonhard Euler would say, what is true for the small numbers is also true for the large. As far as I am concerned, the onus is on them to show that it is not, and not on me to show that it is, as I have already demonstrated what is, and therefore what is not. This method, and indeed any other method, entails a bit of a contradiction, insofar as both the twin primes and the equations used to solve for them are both divergent. So as the twin primes and the gaps between them get infinitely large, by which terminology I do not imply that they are not finite, as some smart jackasses like to quip, but rather that they are large beyond our ability to quantify them. So whether they will still exist or not is in all honesty beyond mine, yours, and any mathematician's comprehension. Corollary. As well as 9a cubed plus 1 minus 1, one must inquire as to what happens when we test 3a cubed plus and minus 1. And lo and behold, we yet again discover even more twin prime combinations, but the rules are a little more complicated, as I shall now try to show. When we test 3a cubed plus or minus 1, we find that what we actually have is 3a cubed plus or minus n and n plus 2, and that the even number input for any one sequence is last digit specific, as you will soon see. So we have 5 basic sequences: 1 even number ending in 0, 2 even number ending in 2, 3 even number ending in 4, 4 even number ending in 6, and 5 even number ending in 8, which therefore increment in tens at each input step. For each sequence we have several n's and n plus 2's, which I will now tabulate along with the n digits of the pair of twin primes, which can be 7 and 9, 9 and 1, 1 and 3. One simple but unknown fact for me till now is that the two odd numbers either side of a pair of twin primes are composite and both divisible by 3 or a power of 3. What we find is that the sequences for any grade of even number are unlimited, as shown by 2, where we see that the differences between the add-ons and minuses is 6, 12, 12, 6, 12, 12, 6, and so on and so forth. I have only given 6 for the grade 0 numbers, with examples of the first 5 pairs of twin primes for each one on the next 2 slides. I shall not give any values for the grade 4, 6, 8 even numbers, and you will have to take my word that they behave exactly the same as the two examples given, or work them out yourselves. The first number in the table is just the order in which the twin primes were discovered. The second number is the even number a input into the equation a to the power 3 plus or minus n. If we subtract 2 from a and divide by 2, then we have the position of the twin primes within the total number of checks, both hits and misses. A little bit of extra mathematical surprise resulted from my timing how long it took one of the sequences to perform sequential blocks of 1000 checks for twin primes, up to 6000 total. These timings are a close fit for the equation 6n minus 1, which are the first differences of the quadratic 3x squared minus 4x plus 2, quadratic with a cubic constant difference of 6. The quadratic is the first difference of the cubic equation 6x squared minus 2x plus 3, the coefficients of the x cubed term being 0. Finally, I would like to express my sincere gratitude to Petra Lastovica for making this superb piece of software, Precise Calculator, available as shareware for free download, and without which this proof would not have been possible. The divisor function is sublime. Thank you.